Hello, good afternoon, everybody. Welcome to our last lecture this semester. Yeah, that's not very good that it's in this form. Yeah, but unfortunately, my professional tasks required me, forced me to be absent on Wednesday. What about the projects and final term? Because first the technical stuff. So the projects, the remark, the final date of the projects was extended to Sunday evening. A few asked for this. Originally, it was Wednesday evening, Wednesday morning. My mistake, but originally it was earlier. Yet some of you wanted it to be extended, and here it is. Still today in the afternoon, so it's Friday when I'm recording this. It will be the marks will be put in the system. The final term is gonna take place on 11th February. I mentioned about it already, remotely over Zoom, with two sets of questions. One set for those of you that passed the first term, and for those that failed the first term and or were absent during the first term. There will be two sets of questions to answer. Okay, if you have any questions, send me an email. I will be on short holiday next week. Still, I'll be monitoring emails and respond if necessary. Then going back to our core issue today. So the final lecture was to have two subparts. So the short market view about the 16-bit world, and the introduction to ARM family. Probably we'll just have the 16-bit world and just an intro to the ARM family without greater details. And about the greater details of the ARM family, you have to wait for the new semester. During embedded systems, we'll be analyzing the members of the ARM family, the capabilities of the ARM family, and the peripherals, simpler or more complex, already next semester. So today just the introduction. So 16-bit world and the introduction. So in case of 16-bit world, the problem of 16-bit today is that there is it's difficult to find a market for the 16-bit microcontrollers today, to be honest, because if you want a simple and efficient microcontroller, then and cheap and low power, then you choose 8 bits. If on the other side you need a microcontroller that will be capable of advanced operations, advanced mathematical operations, capable of servicing multiple peripherals and or operating systems, then you go naturally with the Cortex world. That's the way we do it today. So the 16-bit world, it's basically a matter of a bit of the past, a bit of the legacy, and a bit of the of fulfilling the families. That's those family the wider families of completion of the families of 8-bit, 16, and 32-bit microcontrollers, which is the case of those microcontrollers that I would like to show you, at least briefly. So, in my opinion, there is very limited use of those two families in practice, but maybe you'll find it otherwise. Also, the sense of knowing those families is that you may find a job where, because of legacy issues, some equipment utilizes those platforms. So MSP430 from Texas Instruments and PIC24 from Microchip. And then you will enter this family. So that's why a few words about those two families. So they are, of course, so in case of MSP430, To start with, this is a part of a larger portfolio of microcontrollers that is offered by Texas Instruments, and the MSP 430, which is basically a 16-bit CISC microcontroller, very CISC microcontroller, very pure CISC microcontroller. This family was included in the portfolio of Texas Instruments already some time ago, and in case of this, the existence of the MSP 430, so it is positioned in the portfolio of Texas Instruments microcontrollers in the lowest end. So if you need something cheap, something simple, something power efficient, and still stay within Texas Instruments portfolio, then you have to choose the MSP 430. And then on the a bit higher shelf, there is a Stellaris, and even higher, there is a family of 2000 and above this. In fact, today we have hardly advertised, so fiercely advertised family of Zitara microcontrollers. So Zitara, maybe if we have enough time, maybe we'll talk about them, because they are, at least on paper, very interesting, very fast, very efficient architectures. But more on this already next week, next semester. Yeah, going back to the MSP 430, ultra low power, as the name suggests. Ultra, it's not really so ultra, so the adjectives used by the manufacturers sometimes are used without, sometimes need to be really double checked. So this is the case here. So ultra is not really ultra, but the low power is really there. So there is very nice, we have very nice choices of cores with low power consumption, cores which are 16-bit, which have very nice programming model, but the cores which are not really very efficient, which are pretty cheap, but which are not very efficient. So we talk about up to 25 megahertz only, but here, unlike it's a CISC microcontrollers, it's a CISC core, which means that some instructions are one-to-one, and some instructions need even 7 clock cycles to be executed. Therefore, the efficiency or the performance of the MSP 430 is really deep into 8-bit world, rather than in the comparable with the Cortex, especially M0 and M0 Plus based microcontrollers. In case of the here you can see the wider portfolio of this of Texas Instruments, including as well the DSPs. There is missing, because this is the old picture, so there is missing Hercules line and Hercules line with Cortex R microcontrollers, and as well the families mentioned of Zitara with the Cortex with multiple core applications. But today we're interested in this part, so in this price range, in this budget, in this amount of peripherals, and in this clock that you can see on the slide. So MSP 430, focusing solely on those microcontrollers, are 16-bit. Yeah, it's RISC, but it's my mistake. It's actually CISC based microcontrollers. So that's wrong. This is a CISC based microcontrollers with a lot of intelligent peripherals. So intelligent peripherals, remember, that's the sense of 8-bit cores today, and as well the MSP 430 core, which is not very fast, but if we add if we use intelligent peripherals, they can live on their own, then even mediocre performer, mediocre speed core like MSP 430 would do here, and makes a sense. This is low cost and low power. Internally, the architecture bases on the von Neumann architecture as well, with common address and common data bus, with all the disadvantages of this. So lower performance, but low power and low price. Very important here is the clocking system. here, which is quite extensive, and the clocking system that adapts very easily to the clocking requirements of the peripherals, especially with the view of low power consumption. Very important as well and very strong here are analog peripherals in case of the DMS-430, because those analog peripherals. So we can find some interesting elements here, interesting peripherals like various operating amplifiers. In case of the clocking speed that we can have, it's not something really peculiar. So from 8 to 25 megahertz with the instruction to clock rate ratio from 1 to 1 to 1 to 7. So again, not really very special, although of course the instructions with 1 to 7 clock ratio, clock to instruction ratio is doing more than just very simple adds or on-op operation. The flash memory, the amount of flash memory characteristic for this kind of microprocessor, so from very tiny numbers like 500 bytes to 256 kilobytes. Again, the question is, what's the sense of using microcontroller with just 500 bytes of memory? Of course, only the sense is, and as well with 128 bytes of RAM. Of course, it does have a sense for very low power applications. So come take a look. Although 16-bit core, theoretically at least, the amount of flash and the amount of RAM begins in the regions characteristic to standard 8-bit microcontrollers and the small ones like PIC10 and PIC12, or the 80 tiny, so tiniest of the 80 tiny. So packages, small ones, small to medium size, so from 14 to 113 size. Then the core itself. And what is interesting is that there are two types of cores in MSP 430, 430 core and 430X core. A lot of registers, so it's a feature, rather CISC-like feature, because standard CISC have just two registers. Here, a lot of registers to speed up the operations and reduce the necessity of data transfer on this common bus. But what is pretty unusual here is that in the X core, which is in the larger families, subfamilies of MS230 available, the arithmetic logic unit and the registers are 20-bit wide. 20-bit, not 16-bit, but 20-bit wide, which means that similarly to the DSPs that we'll talk about in a moment, we've got wider arithmetic logic. So the arithmetic logic unit resolution or size exceeding the standard byte boundary. So 20-bit arithmetic logic unit here for the operations beyond 16-bit. So mainly for what kind of operations can we do it? Usually we are using this kind of increased precision or increased resolution, increased size, register size in the operations of multiply and accumulate. But the MS430 is not really suited for this kind of operation. So in general, from my point of view, a small comment is there really a sense of using a 20-bit registers? Why? Because of this. So the registers are very nicely 20-bit wide, so it's okay. So if you stay within the registers, you can have high precision operation, integer operation on high precision, on extended precision, because you can have 20-bit operation. So for fractional numbers, this is suitable, definitely suitable. Yet the problem is with storing or with operation on the memory, because with this 20-bit registers, if you want to store it in the operations in the memory, in general, it eats up 4 bytes of memory. So 20 and from this 32 bits or 4 bytes, 12 bits are just simply unused. So if we consider that the amount of RAM in these architectures, the processors of this series, is not really high, then this is really questionable, this 20-bit operations. Although for sure this is an interesting and discerning feature from the standard MSP430 core, or for example from the core of PIC24. So the competing 16-bit architectures, which is not having this kind of feature. Yet, the question is, should we use it? Then the MSP430, although that's why I rather classify it as CISC, not as RISC, because the architecture here includes addressing modes, and the addressing modes are available actually for every operation. So this is an interesting microprocessor. So the MSP430 and 430X core is that we can use any instruction and use any addressing mode with this instruction. Try to get back to instruction list of Atmels, of AVRs, where instruction and the addressing mode were paired together. So one instruction, the inherent addressing mode used. Here, in case of the MSP430, we've got, from the software point of view, a lot of freedom, so we can pair up any instruction with almost any, because it's not all combinations are available. Yet, plenty of combinations we do have here. So the instruction list is not 30 instructions, 60 instructions like in the RISC microcontroller, but in fact, if you multiply the number of instructions by the number of addressing modes, then you end up with hundreds of combinations that you can have. So you can use register, of course this is the fastest one, so 1 clock cycle, but then you can also use the such strange things as the auto increment, for example, indirect auto increment, where the register is used as a pointer, but then it is automatically increased if the instructions are of byte, word or long word length, for example. So that's also pretty characteristic for this kind of architecture, or for this particular family. Also, it has a support for the low power. We talked about it, so the clocking system is pretty flexible. We can clock the core. Not only we can scale up and down the clocking, but also there are special low power clocks with lower frequency, with lower resolution, with faster wake up time. We have plenty of low power modes. We have this instant wake up, so we can wake the microcontroller up within a single microseconds here, in fact, with this flexible clocking system, because it is what decides about the wake up itself. And as well, there are autonomous peripherals, so the peripherals are not only intelligent, but they can work alone, which means that we can use them without the necessity of the microcontroller microprocessor being run, thus reducing significantly the power consumption. In case of the clocking, the very low power oscillators is something again pretty characteristics for this microprocessor, something I haven't seen in a computing architectures. So the clocking with a very small 20 kilohertz just frequency, giving us the chance to just monitor the registers, for example, at a very small pace, and to wait for any event to happen. And then when the event happens, then we just switch to the DCO, digitally controlled oscillator, with easily tunable clocking frequency up to 25 megahertz, so depending on the architecture. So we don't need to use RTC. We don't need to use, because in other architectures the role of a low power oscillator sometimes is possible with the use of RTC clock, so this 32 kilohertz clock, yet it doesn't have to be so. So in those kind of architectures, we just either switch off the core or clock it with few megahertz. Here we can clock it really slow. Of course, the signal processing has no sense at this clock rate, but monitoring of registers and configuration of peripherals at this clock rate, why not? Why not? And then the low power modes, plenty of low power modes in practice. So we've got the standard active mode, but then we've got the stop mode, standby mode. We're analyzing this table during the lecture of low power embedded systems, so low power microcontrollers. So we will not repeat it. In case of peripherals, something the peripherals in general are, I would say, standard to 16-bit families. So it's comparable to XMIGA. Because we've got, for example, onboard DACs, we've got DMA, we've got hardware multipliers, but also these analog peripherals are interesting. So the analog comparators, the ADCs, maybe not very special, but still we talk about small performance 16-bit family, so the 12-bit ADCs, very good here, so sufficient here. But we've got the operation amplifiers, and in case of operation amplifiers, yeah, there is the RF front end from the analog peripherals, which means that we can use it as part of Internet of Everything or Internet of Things as well, because one core does it all. There is a support for LCD from special things. If we talk about the RF communication, then AES as well available, so the security block necessary for certain protocols, like for example the SSL on top of the Wi-Fi, or on top of the thread protocol. So various things like this. In case of the op-amps, I think there is a slide about it. Here is this family in more details, because we have in fact four subfamilies, so hundreds, 200s, 400s, and 500s. The lowest and the smallest is the MSP530 with the 1XX family, where the speed is limited to just 8 MHz a clock. Flash memory, small one, so single kilobyte to tens of kilobytes. Maximum RAM as well, only up to 10 kilobytes. Small cases because 14 to 48 GPIO pins, but still, even in the smallest configuration, we can have the DMA. We do have this 12-bit ADCs, 12-bit DACs, and we've got multiplying unit, hardware on board multiplying, and software, and the SVS system, so the monitoring of the power supply. All this, so of course, higher families have more things. With the largest family, still pretty small. So take a look, just 25 MHz maximum clocking, maximum flash only 256 kilobytes, maximum RAM only 16 kilobytes. Also, the number of the amount of GPIOs, not really the large one, so 83 for 16-bit microcontrollers. Believe me, not something that we do. That's outstanding, or that's something unstandard. Here we have this RF block available sometimes in some units, USB in some units, this security block or coding block in some units. In all the units, we've got things like DMA, for example, from the important stuff, or multiplier. In case of the op-amp, that's why I mentioned about this block, because some microcontrollers from other manufacturers also include the op-amp block. Yet the op-amp block in the MSP430 is, in my opinion, superior because of the configuration capabilities. So here you can see the schematic. So what can we see here? We can see the op-amp itself. But the op-amp, as you should already know, can be used in various configurations. Here in this microcontroller, the configurations are, here are the configurations. So it can be configured as general purpose op-amp, as a gain buffer with unity gain, as a comparator, and in non-inverting and inverting PGA. PGA stands for programmable gain amplifier. Thus, we also can have a differential amplifier. So all those basic configurations, so we have no special configurations like transimpedance or filter, or I don't know what else can be the integrator, for example, or logarithmic amplifier. So nothing like this here. But let's not exaggerate. It's just a microcontroller. So basic signal conditioning can be done with this kind of amplifier as well. We have usually more than just one, which means that we can chain those amplifiers, so we can form some instrumentation amplifier configuration here. All this is possible. This configuration is possible. This configuration is possible with the this configuration is possible with the because of the existence of multiplexers, various forms of multiplexers here. In fact, by changing the registers, the values, the values or the configuration, desired one, automatically the multiplexers are being switched, forming the desired op-amp. Naturally, there is a problem with the op-amp used in the microcontroller about its parameters, so it's pretty noisy. And the bandwidth is pretty low, so it means that you can use it for only for conditioning of not very not very sensitive signals. Still, it's better to have it than not to have it. So it's all configured in analog, meaning that we can, of course, use the MSP430 with such op-amp blocks on boards with a much lower elements count than the normal microcontrollers, because we can really integrate easily the necessary signal conditioning already within a CPU or MCU. That's planned out here. You can see possibilities of configuration, so it's possible, as you can see, to configure those op-amps into instrumentation amplifier configuration with fully differential input. So the advantage of this configuration is that the impedance seen on this pin and on this pin is as high. So for very sensitive sensors, this configuration really must be used, or is advantageous over the standard one. The second 16-bit family that we can find today that is actively used and is pretty popular is the family of PIC24. This PIC24 as well, like the MSP430, it's the it's the supplement to the family of PIC microcontrollers. Its position is this time not as a low end, which was the case for MSP430, but in case of PIC24, this family is positioning in the middle of the family, so between these small 8 bits, so PIC 10, 20, 12, 16 and 18, and the high end in case of microchips, so PIC 32. In case of PIC24, we've got in fact 4 subfamilies. So 2 of them are mentioned here. So this is the PIC24F, PIC24H. So the low end and high end 16-bit microcontroller. But additionally to this, we've got DSPIC, the families which are known under the name of DSPIC. DSPIC stands for digital signal processing. That's why I don't have it here, because these are formally digital signals controllers. And again, if we have enough time next semester, maybe we'll talk about the features of the DSP of the signal controllers, digital signal controllers, and how they stand against microcontrollers and against digital signal processors. But formally, again, so depending on the classifications, we can classify them as a separate subfamily, but we can classify them as part of 16-bit portfolio of the microchip, standing a bit lower, a bit higher than PIC24, 24H. So there are 2 subfamilies of DSPICs, all of them having 16-bit core, but signal processing peripherals included. In case of this PIC24 architectures, and this is modified hardware, so similar to PIC18, for example, but this time we've got 16-bit arithmetic logic unit, 16-bit registers the amount of flash, SRAM and EEPROM. Standard, again, comparable to MSP430 and comparable to ATX Mega. So nothing really special here. What is a bit different is that comparing to MSP430, maybe is that we have the DMA channels, more DMA channels. Of course, we've got standard 16-bit timers counters. The case is as well similar to MSP430, so 14 to 100 pin. From the block diagram point of view, the PIC24F delivers 16 MIPS performance with the 7-bit by 17-bit multiplier on board, with barrel shifter on board already, so the single cycle division by 2 to the power of n is possible here. As well, extensive support for sleep mode, plus the standard set of peripherals, so the I2C, SPI, UART, analog comparators, 10-bit ADC, also possible charged time management unit for touchscreens or for capacity buttons, things that you can find already in PIC18s, but USB it's optional is there. In case of the 24H, major difference DMA, so like in the 500 family of MSP 430, so the DMA block available, but here point at this difference, 40 millions of operations per second, so much faster, so about twice as fast as the fastest MSP 430. By comparison, also CAN is available here, together with 12-bit ADC, although this is not really different from the MSP 430. Also, there is a feature of peripheral pin setup, which means that we can change the positioning of the pin, of peripherals on the pin in a limited fashion. Yet it is possible. So today, when we are accustomed to STM32s, to be honest, this feature does not seem to be so outstanding. But coming from the world of AVRs, where peripheral of, for example, UART has dedicated pins which you must connect to when designing a PCB board, this peripheral pin select was something fresh, something special. Today, really, not really. Today, it's just a standard feature. This peripheral pin select, but it used to be something extra in the past. In case of the peripherals, this PIC24 is the idea of using 16-bit microcontrollers comparing to 8-bit is to use them in motor control, so especially in PMSM or BLDC, so brushless motor control. And in case of those motors, first of all, we need to be able to drive extensively, use the PWM features to use the timers. But second thing is that those PIC microcontrollers, so in case of microcontrollers, we must be able to calculate, so to measure the current flowing or the voltages, and then to make some transformations which are required for PIDs and for calculating the PIDs functionalities. Therefore, the 16 bits sometimes they have an edge over the 8 bits in this application. Of course, today it's really questionable. So today it's better to use, in my opinion, Cortex M0 or M0 Plus based microcontroller for this kind of operations. Yeah, but still, again, sometimes the motor control, lightning, metering, three-phase energy metering application, switching mode, power supply, they can be constructed with the use of PIC24 and the peripherals in the PIC24, so the PWM, 16-bit timers, ADC, DMAs, DACs, also those peripherals classify the PIC24 for the usage in this kind of applications. Yes, in case of audio, that's maybe less that's maybe less important. Finishing it, the major problem of 16-bit family is the existence of ARM family today. So 10 years ago or 15 years ago, the 16 bits were a natural extension of the 8-bit capabilities, especially in the applications where not only peripheral control but also some calculations were required. Yet, in the so-called meantime, so during those last 15 years, on the market they appeared a very, very strong player. So these are the Cortex M cores, the microcontroller, 32-bit microcontroller family, the family that is much more complete, and much more united, or than the PIC24. So the same tools can be used, and same architecture actually is available throughout starting from the small microcontrollers to very fast in case of our family, which we can't have in both the MS-5430, because MS-5430 and Stellaris are completely different families, using different tools, requiring different tools, and requiring analysis of completely different documentation, because it's a completely different instruction set architectures between them. In case of microchip family, it's closer, so there is some MPX lab IDE, so development environment of microchip is same for 8-bit and for 16-bit families, but still the families are different. The ARM family, one of the major advantages of the ARM family, comparing to the 24-bit PIC24 and the MS-5430, is that we've got same set of tools. If we are programming the very tiny, very low power or ultra turbo low power microcontroller, and as well if we program a digital signal processor or digital signal controller beast with 1,000 or more millions of instructions per second, and still one tool. And that's one of the strongest feature of the ARM family. What is ARM family? So just to introduce you to the subject. So formally, the ARM is the 32-bit RISC architecture developed by ARM Holdings in the 1980s. So the ARM, ARM Holdings were the authors of very popular in the 1980s processors of 6502, 6510. So the processors found in computers, small computers of those times, Commodore 64, Atari. So they were all based on the processors, 8-bit processors, developed by this company. Yet the company then changed their view on the market, so changed their business model, and they developed the architecture, which they since then are licensing. So they are not really producing any hardware, but they are just licensing the architecture to anybody that likes it, to anybody that wants it. And today they have in partnership more than 90% of the 32-bit market. In case of microcontrollers, they're a hegemon today, so there are only a few architectures left which are not ARM-based, so like microchip, PIC32 or RISC-V, which is in open architecture. But all the other competing architectures are really a niche on the market. So all the major players today are using the ARM. So even Texas Instruments today, Texas Instruments with a huge history. So remember that this is the origins of microcontrollers. We know the origins of of the DSPs. We know were made by Texas Instruments in 1970s. As well, the funny stuff is that the Intel, with of course a lot of money made on their own architectures of 8086 architecture, on all these Core I's, R5, 7, 9, whatever they are producing. So we have a huge portfolio and plenty of money. Still, they gave up on microcontrollers. They were trying to introduce their own ideas about how the 32-bit microcontrollers should look like. Today, Intel also includes the ARM core in their microcontrollers. So it does mean, for me, it's a proof that how successful the ARM architecture is, in fact. So everybody today, in fact, every company dealing with microcontrollers utilizes at some point in some of their products a version of their Cortex-M core. Best companies also utilize the signal processing cores and application processing cores, so the Cortex-Rs and Cortex-As. But it really depends on the application. But we are interested in Cortex-M cores and in the structure of this architecture. So maybe skipping the details, the first core that's speeding up a bit. In case of the Cortex-M core, the history, of course, began in the end of 1980s with a few trials made by the ARM company or ARM Holding, whatever it is, to introduce the instruction set architecture, various instruction set architectures. Yet the first really successful instruction set architecture they introduced was the ARM7 TDMI architecture. Still, you can find the market microcontrollers based on the instruction set architecture of ARM7 TDMI. What was characteristic was that this architecture included, first of all, three-stage pipelining. Second of all, in this architecture, we did have additional instruction set, 16-bit instruction set of time. 16-bit, because the idea here in ARM7 in general is that the width of the bus, of the program bus, means the width of the length of the instruction. So we have all the instructions have to be read in one clock cycle, unlike in MSP430, for example. But the same like in PIC 10, 12, 16, 18. Remember that in PIC 18, the width of the bus was 18-bit in order to be able to read one instruction in one instruction clock cycle. Here in our 7 TDMI, it's the same exactly. So the core reads one instruction in one clock cycle, at least the ARM7 TDMI, because the newer ones are even better, so they can read 4 to 8 instructions into one clock cycle. So compare in PIC 1 to 1, in MSP430 4 clock cycles sometimes are required to read one instruction. Here 1 to 1 or even 4 or even 8 instructions read in one clock cycle. So that's one of the underlying of the feature why showing us one of the elements showing us why the ARM7s are so fast, or in general the Cortex microcontrollers are so fast. But take a look, what is even more interesting is that we have 32-bit microcontroller. Originally there was the 32-bit, so one is all instructions were 32-bit, but in ARM7 TDMI there was a revolution because there were other instructions which are just 16-bit wide. Yeah, think about it how to do it, because then it's a 32-bit microcontroller with 32-bit registers, yet one instruction just 16-bit. How on earth can it be done if in a stupid, small, tiny PIC18 one instruction is 18-bit and here 16-bit, and the width of the register is 32-bit, and in PIC18 of course it's just 8-bit. So here is a bit tricky thing. There is a bit tricky thing about this. More explanation already next semester. How does it work? Also interesting thing not met in the microcontrollers thus far are the 7 work modes. Also something new. 7 work modes. Here are the work modes. So we have the work modes are the element from CPUs, from microprocessors, large microprocessors. They were introduced to the world of microcontrollers with this ARM7 TDMI architecture. Today, they are still in use in the larger or medium-sized Cortex-R and large-sized Cortex-A microcontrollers. In Cortex-M, so in the microcontroller cores, only a subset of this cores prevailed. in fact, yet it all began in ARM7, TDMI core. Additionally, what was special about the TDMI, so the thumb instruction list, there was a special thing introduced here that stayed with us, was extensive debugging capabilities. Now again, when you use the ARM7 or Cortex core, you take it for granted that there is a debugging, easy debugging through SWD, and that you can see and monitor a lot of registers, a lot of memory addresses at the same time, but it wasn't this way. And in 8-bit microcontrollers, it's not that simple. It's not this way. So try to debug, even using a JTAG interface, try to debug the AVR. It's way more difficult. Here it is available from ARM7 TDMI and to all newer versions. There was also a multiplier, hardware multiplier. So again, it was, you remember about the time, this is 1990s, so then again, hardware multiplier was not something common today. This feature is not, doesn't seem so important, but still important is the extensive support for interrupt. We talked about 8051. In 8051, the single amount of interrupts. Here, from the start, hundreds of options, and today even thousands of possibilities of possible events that are serviced by the core itself. So a huge difference and a huge improvement in case and the ease of using the event programming model applications. So that's the ARM7 TDMI major features. Physically on board, this is a core. So remember that the ARM7 TDMI and the Cortex cores are just simple microprocessors. These are not microcontrollers, these are microprocessors, which means that they don't include any peripherals. All the peripherals have to be connected somehow. We can try to connect them by ourselves today. So if we talk about programmable logic, then in programmable logic we can use, for example, Cortex M1 or Cortex M3 today. And then you will have a chance, if you decide to do so, to connect all those pins that you have on the right on the slide manually. Yet normally when you buy a microcontroller, hardware microcontroller, then usually it is connected, so the peripherals are there. And we are, by microprocessor, we talk about only this part. So 32-bit arithmetic logic unit, of course, hardware multiplier, hardware bar shifter there, plus a lot of registers. This is standard thing, so 31 registers. Theoretically, a lot of registers. In practice, the amount of register is pretty. It's not that large because although we've got 16 registers. Formally 31 registers in the ARM, but for the use we have in fact just 13 registers. 3 registers are booked for special use, for program counter, for stack pointer, and as a link register. So it's not all that rosy. So in fact the amount of registers is not as large as it seems at first sight. Still quite a lot of registers available. In case of the instructions, interesting thing about the ARM instruction set, the thing that was very characteristic to ARM architectures, at least in the 1990s. So for me as a newbie then in the world of microcontrollers, as the guy that was accustomed to the 8-bit 8051 and PIC microcontrollers, the instruction list was a very unusual. What is unusual here? A couple of things. Of course, the first thing is that the ARM instruction list, one instruction 32-bit, so no other size available. Second unusual thing, conditions. So first 4-bit are same like the 4-bit in the status register. Where was the status? Here is the status. Take a look. The status register, of course, in the status register we've got couple of things, but we've got the results of the previous operations on the NZCV bits, so -0 carry and overflow, and this fits here. It means that the instruction was checked, so the instruction was executed or is executed, because this instruction list can still is still in use. The instruction can be executed if the conditions are met. If the previous operations gave false result, then the results are false. The comment is not executed. So in fact, integration of some conditions within a simple, for example, multiplying instruction. And the third unusual thing is that plenty of registers. So take a look, we've got N, D, and M. Because here the instructions, unlike the 8-bit microcontrollers, most of the instructions have source registers which are not altered during the operations. So the destination register, which is different from source register, so that's what RD means. So the destination register, which is different from the source registers. This is again a feature, unusual thing. Unusual thing not met in other microprocessors. In case of thumb instruction set, a couple of things were stripped. Out of it, there are a couple of limitations in order to make the instructions smaller. So instead of 16-bit, 32-bit per instruction, we've got just 16-bit instructions. So we've got a couple of things that we changed. One other thing is that the condition bits were erased. So there is no conditioning right now, which means that this thumb instruction set is less effective. But in case of execution time. But what is more effective, what people like about the thumb, is that we've got code density, which is twice as high. Because instead of reading 32-bit instructions, we just need to read 16-bit instruction as well. In case of microcontrollers, we can have, if the program bus is wider, then instead of reading, let's say, 4 instructions with 128-bit read, we can read the ARM in 128-bit data with 128-bit read. We can read 4 instructions at once. With thumb, we can read 8 instructions, meaning that half of the reading is necessary. Here, speeding up a bit the communication with memory. So from one perspective, thumb instruction list is slower because we have to use more instructions usually to do the same than in ARM instruction, using the ARM instruction list. On the other side, the thumb instruction list gives us higher code density, and the thumb instruction list gives us faster access to memory because we don't have to wait for the memory as long as in case of reading the 32-bit instructions. All in all, there are pros and cons, but in fact, the thumb instruction list is a very interesting idea. So interesting that today in our microcontrollers, Cortex-M microcontrollers, there is a mixture. So there is so-called thumb 2 instruction set, where some instructions are 32-bit and some instructions are 16-bit, and only this instruction list is used today. Only this instruction list is used today in Cortex-M microcontrollers. In application processors in Cortex-A today, there is used as 64 instruction list, which is in fact 32-bit instruction set, not 64. But formally it is called A64. But about this when the time comes. And to finalize outside, so maybe let's keep these features, we'll talk about them a bit later on, so during next semester. Just to finish the lecture, finalize this picture actually this picture first. So 2 slides. First slide showing the families that we have and showing only part and a subset of microprocessor cores that we have today. So ARM7 evolved into Cortex family. There were some 7, there were some 9, ARM 8, 9, 10, and 11. So those cores were used. For example, first iPhone was built on those ARM9 core. Yet this evolved into Cortex family and into 3 Cortex branches: Cortex M, Cortex R, and Cortex A, plus some secure cores for security applications. Yet the Cortex M are the cores for microcontroller operation in view. So as a replacement of 8-bit, 16-bit, and 32-bit microcontroller, really doing the job, really outpacing anything we have on the market, and making a complete family of microcontrollers. And then we've got, if this is not enough for us, we have an upgrade path to a bit different, but still within the same family, Cortex R, which are basically used in security applications and in this digital signal processing application, because it wants to be a replacement for a DSP processor, and by some manufacturers, the Cortex R cores are used for this. And on top, we've got the application processor, so Cortex A's with competition to a classic microprocessors like the Core i7 or Core i5 from Intel. From our perspective, interesting is the smallest family, and in the smallest family, we've got a complete portfolio of microcontroller cores. So starting from very tiny Cortex M0, which, as you can see here on this slide, can be built only with 90 micrometers. It does require only 90 micrometers or left of silicon. So it can be built into even small sensors, and this is really happening today. So the Cortex M0 is either can be found as a standalone microcontroller, as a base of a standalone microcontroller. Same as Cortex M0 Plus, which is a bit more efficient with slightly extended functionality. Details will follow next semester about it. Cortex M0 is a core with basic functionality. And again, it can be found as a standalone microcontroller, but can be also found today built in as a coprocessor, as a part of an intelligent peripherals. For example, in the microcontrollers with radio frequency functionality to where this kind of core is responsible for implementation of the some layers of the communication protocol. Then we've got the Cortex M3, which is the Cortex M3 core, which was the first core appearing on the market from this family. The core that was directly comparable to the ARM7 DMI, the core which was available with about 100 up to 100 megahertz clock rate. The digital, the fixed point core, so with the integer only support for integer operations, but 32-bit integer operation. So the standard 32-bit micro, the heart of the standard microcontroller, 32-bit microcontrollers today. It can be found. So in many applications, not requiring floating point or extensive calculations, the Cortex M3 is part of these calculations. Then we've got the Cortex M4 as the next, so the upgrade from the M3, including signal processing instructions and including the vector operation, and including the floating point operation. So the M4 being an excellent upgrade to the M3 towards the signal processing applications. And on top of this, we've got the M7. We've got the M7 today with super scalar architecture, with very high clocking today, with dual precision, double precision floating point, with the lockstep operation capability, with the AXI bus, with TCM on board, so tightly coupled memory, with cache on board, with extended pipeline on board, giving us today, that's the situation, giving us today really 1000 beyond 1000 MIPS processing speed. So huge calculation power, and all this in a very small form factor, and all this in a very with a very tiny power consumption, really very tiny, of course not as small as Cortex M0. So these are processors for completely different use, but delivering a super performance. This processor today is capable of implementation of artificial intelligence and image recognition face recognition, for example, of course, for audio processing, voice recognition. All this can be done today on Cortex-M7 based architectures. But so additional to this, so this is not a complete portfolio to this, because additionally to this, here, and a bit here, we've got new cores. So M32, 23, 33, 35, and 55, which add to the fantastic throughput and simplicity of the core existing M3, 4, and 7 cores. Additionally, security features, various security features, which are really important in many applications today. So we will talk about this already next semester. Why the security is so important today, even in the world of small microcontrollers, and this is also addressed today more and more by the ARM, with the inclusion of this additional secure Cortex cores in their portfolio, as well as Cortex M55 being the new standard, or becoming the new standard, hopefully, for support of machine learning and artificial intelligence. So again, the feature that used to be a feature in large programmable logic or microcontroller with application microcontrollers. Today it goes down to a microcontroller world, helping us in delivering to the market very sophisticated applications, still with the use of this microcontroller from the ground, microcontroller core. So it's extremely interesting. Summing up, it's the Cortex microcontroller. It's an extremely interesting family of cores, compatible, so upward compatible with each other. So whatever you write in Cortex M0 is supported by Cortex M7 or M55 even, giving us a huge choice of performance and of microcontroller size within CL1 family. And as well, the next strong part of the Cortex family is that really thousands of companies are delivering chips with the Cortex core, meaning that we have a fantastic choice. We can choose NXP families, we can choose Texas Instruments, we can choose ST, we can choose analog even devices as our supplier of microcontrollers, and they will still be within Cortex, inside of Cortex M core, inside any Cortex M core, and you can program all of those microcontrollers delivered from different manufacturers with the use of Kyle and of Kyle programming environment, and with the use of CMSIS as the software support layer. So this is really plenty of good things to be covered, but about all those things already we'll talk step by step during next semester, so starting in March. Hopefully this time we will see each other throughout the semester, not like this semester only for part of our meetings. So that will be it for me for now, for this offline lecture. Thank you for the whole semester, and hope to see you already during final time. Thank you very much, and have a nice day, and good luck on the final term. Bye bye.